Is it going? Okay. Alright, we're going to do some examples here of some UCM problems, which means uniform circular motion. Okay? In other words, nothing's really speeding up as it's going around the circle or slowing down. Later we'll do stuff with that, but not right now. Okay, so we did this one in class or on the other video. We're going to start down here. Some of these I'm going to do all of the way out for you, and you just need to take notes. And some of them I'm going to start, and you need to finish them. So example 5.2 is very similar to example 5.1. So I'm just going to start it for you. Okay, the moon's nearly circular orbit around the Earth. Got the radius, and we've got the period, which is a month. Okay, so capital T, that's time, but it's a special time because it's one time around, all right, period. Okay, determine the acceleration of the moon towards the Earth. So we are going to do v squared over r again, and it is an AC, centripetal acceleration. Okay, so the radius, we got that, okay. Don't forget to convert it to meters. And then the velocity, we've got to find that. So since this is UCM, V equals d over t for this. Alright? Now the distance is going to be circumference. And we're just talking once around. Up here we were doing twice around. And the time over here is going to be a month. Alright, I'm going to let you do the rest, okay? Any other places you could run into problems with this? Not really, as long as you convert this to seconds, okay? It's obviously given to you in days, so got to be careful of units. Okay, so I'm going to give you the answer. The acceleration is 0.0027 meters per second squared. Alright, now the moon's going really fast, but the radius is huge. Okay, so you get this small centripetal acceleration. Alright, you prove the answer, and we'll turn these in class next time. Okay, example 5.3. Estimate the force a person must exert on a string attached to a ball, just like over here, to make the ball revolve in a horizontal circle, same radius, same revolutions per second. Okay, I'm going to let you do this one completely. Up here, remember, we already got AC, so think about what you need to do down here to get that to force. Okay? Alright, also I'm going to put this, tell direction of the force. Okay. Alright, direction's important. Okay, let's go on to some more complicated stuff. This one we're going to do in lab, if we haven't already. Okay, the game of Tetherball. It's a ball on a string. Okay, this is a conical pendulum, is what it is. In what direction is the acceleration of the ball, and what causes its acceleration? So most of you have played Tetherball before, probably. We've got a pole, and then we've got a ball on a string, and it goes around in a circle. Now the radius of that circle can increase and decrease based on the speed that it's hit with. Okay, so we have to understand the FBD on this very, very well to be able to do our lab. So pause the video and do the FBD on your own, and then unpause it and check and see if you were right. Okay, go. Alright, here's the FBD. We'll get a different color. So we got mg down. and then we've got tension up here along the string. That's it. That's the FBD. Now if this is a test, you can't draw the components on there because they are graded as extraneous forces. So that's what you would put. But we're going to add the components because we need them. So up here I'm going to say that this is theta. Alright, and I'm going to draw in a y-axis. And I'm going to draw in an x-axis like that. And I'm also going to put theta right here. Okay, because this line and this line are parallel, we know that this angle and this angle are the same. Okay? Yes, Melissa?
Could we put theta at the bottom by the ball?
Okay, you could put theta down here at the bottom by the ball. That's right. Okay, and that's going to change a couple things over here, and I'll show you in a second what that does. I just chose to put it here and here. Arbitrarily, really, but yeah, you could put it down there. Good question. Okay, now we need to figure out in what direction is the acceleration of the ball and what causes its acceleration. Notice I did not put FC on this diagram. We never put FC on an FBD. Okay, because FC just comes from other forces or the components of other forces. Alright, so let's put the components of tension on here. Tension's got an X component and it has a Y component. So we need to be able to deal with both directions. In the Y direction, the Y component of tension cancels out mg. So I could say F net for the Y direction equals 0. And that's not part of the question here, but this is very important for our lab, understanding this piece. Okay, I could further say that mg is equal to this component of the tension. Okay, now it's difficult to see, but if we're using this theta right here, this component right here could also be drawn right here. Okay, this and this are the same. So this is t times the cosine of theta. Okay, so mg equals t cos theta. Alright, now Melissa's question was if we put theta here, then it would be t sine theta. That's how it would change it. Okay, and it would still be right. We just have a different value for our angle. Alright, now what about the F net in the x direction? F net for the x direction is equal to Fc, the centripetal force. Okay, now the centripetal force in this problem is not caused by tension, it's caused by the horizontal component of tension. So I can go over here and I can say Fc is equal to tension sine theta. Okay, so if this is theta up here, this is the opposite side, this is the hypotenuse, so this right here is t sine theta. And I'll label that on here. T sine theta. Okay, or we could also draw it up here if we wanted to as well. It would still be the opposite side. Okay, so I can then kind of answer this question. What direction is the acceleration of the ball? What causes it? Well, this goes to mv squared over r equals t sine theta. And I can say v squared over r is equal to t sine theta over m. Alright, this is the acceleration. It's a centripetal acceleration. So I can say AC is inward and caused T sine theta. Alright, it's going to be caused by the component of that force. Okay, this we did in class. Or it'll be in the other video if you were absent or something like that. So we're going to skip down to this one. Okay, but first I think you guys deserve a slang flashcard. Roll deep. What could this mean? To travel in a large group of people. Friends, associates sometimes appear to be tougher and more popular than they actually do. And then there's all these synonyms. So, place where it might be used. Maybe a business meeting. I see that you too roll deep. Yes. Try and put that in your daily vocabulary. Okay, next question. A rider on a Ferris wheel. Okay, so it's going to move in a vertical circle, radius r, and here's the key, constant speed. Okay, this tells us that we are in UCM. Okay, so the normal force that the seat exerts on the rider at the top, less than, more than, or the same as the force exerted at the bottom. Okay, we have to draw our circle, and then we've got to draw an FBD. Here's the top, here's the bottom. Okay, so pause, draw your own FBD at both places, and then see if you're right. Okay, here's the FBD. mg is the same in both places. This is the person's weight. Alright, since the speed is constant and the radius is constant, that means that AC has to be constant because AC is v squared over r. Person's mass is constant as well, so that means FC has to be constant. In other words, the inward net force, mv squared over r, is staying the same the whole time. Okay? Now, to keep it the same the whole time, normal force is going to have to change. So, what we've got happening here is at the bottom of the ride, normal force is going to be bigger. At the top of the ride, normal force is going to decrease. Okay? Now, if you subtracted and subtracted here, you would get the same answer for each to keep F net the same. Alright, and this makes sense in reality. If you're going up over a hill, the seat is not pushing up on you as more because you feel like you're kind of lifting out of the seat. If you're at the bottom of the ride, you feel like you're kind of sinking down into the seat, and that sinking feeling is the feeling of the seat pushing up on you harder. That's normal force. Okay, so we basically just explained the answer. Okay, the answer is, let's see, exert. Top of the circle is less than the bottom of the circle. Alright? And we might want to say this, F net is constant. Okay, and that would help us explain it. So we could say FC, this is top, FC is equal to mg minus normal, and at the bottom FC is equal to normal minus mg. Okay, let's rearrange these for normal. Here, if I add normal to the other side, I'm going to have normal is equal to mg minus fc. Alright, here, if I put mg over there, it's going to come out as normal is equal to fc plus mg. Okay, so here you can see that we're adding the two forces to get normal. Here you can see that FC is being subtracted from mg, okay, thus making n bigger. So here's kind of the conceptual proof of it. Over here is the algebraic proof. That holds true when FC is constant. Okay, it's not changing in this one. All right, last problem. I'm going to do part of this for you, and then I'll have you finish it on your own. Okay, cars going around curves. Very important physics right here. So we've got this track or road, and we've got a car going, let's say it's traveling in that direction. We've got the radius, we've got the speed. Will the car make the turn or skid if the pavement is dry? Okay, and we've got mu static around this curve. It's 0.6. Yes, Abby?
Why is it mu static if the car is moving?
Okay, that is a great question. So yes, the car is moving, so you want to say, oh, it's kinetic friction, right? Okay, the reason why it's static is because we are talking about the wheels sliding across the pavement. If they slide, we are talking kinetic friction. Okay, but those tires are not sliding, they are gripping the road and rolling across it. And so that's actually static friction. It's the same if you're walking. When you're walking, if you have kinetic friction, it means your feet slipped out from under you. If you have static friction, it's like you're normally just walking down the hall. Okay, you're not usually slipping. So static friction is what we want. And we also know, by the way, kinetic friction is lower than static friction. So we don't even really have to look at the kinetic friction if the thing is sliding. Okay, so here's what we're doing here. We, from these numbers right here, can figure out the centripetal force needed to keep the car on the curve. Also from these numbers, we can use the fun equation to figure out how much friction is actually going to act with. And then we can compare them. So we're going to do FC equals mv squared over r. Let's do that first. Okay. So we have all the numbers. We've got 1,000. We've got a velocity of 13.9. Square it. And we've got a curve radius of 50. Okay, let's punch that into our calculators. And if you do that correctly, you will get 3864. Alright, I'm not going to round it for now. I'm not going to worry about sig figs. Okay? Now, here's the deal. Just because we calculated this number does not mean we get that number. Does not mean the road will provide that many newtons. That's a big misconception when studying this. This is what is needed. Okay, now will we get it? We need to figure out that using the fun equation. Force of friction is equal to mu normal. Okay, we could also put Fs there, meaning static friction. So force of static friction is equal to our mu of 0.6. This is a flat road, no banked curves or any craziness. So normal is just going to be mg, 1,000 times 9.8. Alright, you punch that into your calculator, you will get 5880. Force of static friction equals 5880 newtons. Okay, now remember, static friction is a lazy force. This right here is the maximum. So we only need this, but static could give us up to that. So static friction is actually going to match this, and it means we could go a little faster on this curve. Okay, not that we would want to. We're smart drivers, right? But we could go a little faster and still stay on the road. Alright, I think that's all we need to say about that one. Okay, now this one right here, I'm going to have you finish that one, and I will grade that as part of your homework. So thanks for watching, and I hope that this was helpful.